Alright, so here we are with transformations and stretching and compressing. Alright, so the first thing we'll talk about is a vertical stretch or compression, so that's up or down. And technically our piece in here is the A value that we're focusing on. So again, we've already done H, which was left and right, and K, which was up and down. And now we're talking a little bit about A. We did also do A in our last lesson where we flipped it over an axis. But this time we're talking about not only flipping it over, as you can see in the image here, over the x-axis. We also have the idea that we can now stretch and compress. So, if you see a value out front here and it happens to be a negative, that's going to do your axis flip. But if you also see that number and it is between 0 and 1, you're actually going to vertically compress. So if you imagine kind of holding on to the ends of this, or well, actually this is the parent function here. If you imagine this like a string or something and you're holding on to these strings, but you're compressing down. That is where, again, vertical, so down, that's where you're kind of widening it, right? If you push down, kind of like Play-Doh or something. Also, if you imagine kind of it sticking here and pulling up, that's your vertical stretch. And so that's if this A value happens to be greater than 1. Because if it's equal to 1, then that's right here at the parent function, okay? But if you have any numbers that are between 0 and 1, that's going to be your vertical compression, and then greater than 1 is your vertical stretch. Same thing happens if it happens to be a negative. It's just that after it flips across the x-axis, it will then stretch or compress. So, same problems here. It's between 0 and 1. And then if things are greater than, in this case, -1. And so that's actually why if you ever look at different notes for these concepts, they'll say not only that A is between 0 and 1, they'll actually say that the absolute value of A is between 0 and 1. And that's because then they can take over this entire statement in just one piece. Okay. The next is true for the other one. Again, other than just saying A is greater than 1 and only talking about positive numbers, they'll include the negative numbers by saying, hey, if you actually take the absolute value of that A, you end up with, a little smiley face here, you end up with all of the numbers greater than 1, and that's going to stretch it. Okay? So that's the idea, and of course, other than vertical, we have horizontal. So our horizontal stretch would be like your horizon, so across, all right? So horizontal is going to be the number, of course, that's inside the x. And so we need to watch out for this one because, of course, instead of having a compression at between 0 and 1, they've actually got a stretch, okay? And again, that's because inside of here, if you remember our last mention when we talked about H, this is your funky town. Okay, and so what happened, of course, with the A is basically flipped for the B value. So in that case, if you have the absolute value of this B and it happens to be between 0 and 1, you're going to end up with a stretch. And this is a horizontal stretch. Versus if you come up with a number that is larger than 1, you're going to have a compression. And again, usually when you think of numbers that are larger, you think of stretching things. But of course, in Funky Town, that's going to actually compress. I also like to talk about these as different words. For instance, a lot of times I'll talk about these as being, that's not the word I'm looking for, fractions. Okay, but of course, the problem with saying fractions is that 3/2 is a fraction. And 3/2 is actually greater than 1. So when I say fractions, I don't literally mean fractions. I mean numbers that are less than 1. I usually think of those as fractions. So, sorry if I confuse you. And then the other ones I usually think of as whole numbers. But again, whole numbers are things like 1 and 10, but 10.2 could also be a compression in this case. So maybe I should refer to them as larger numbers or whatever. So either way, those are the words that I'll sometimes use, so we have a reference for that. So taking a look, another thing that's interesting about this is that anytime that you are looking at an A value or a B value, and you are talking about being a fraction, if you will, all right, you are going to end up making that visual the same. Okay, so if you have a fraction, you are actually going to have this wider looking thing. All right. If you have a if you have a number that's greater, actually we can do it on this page, than 1, or the absolute value of it is greater than 1, then we're going to have this compressed looking feature, okay? So the idea is that when you say there's a vertical stretch, that's actually the same as saying that there's a horizontal compression. So if you do the opposite of vertical, which is horizontal, and the opposite of stretch, which is compress, you end up with the same statement. That's the same for over here. So if you ever have a vertical compression, that's the same as saying opposite of vertical, which is horizontal, and compression, which is stretch. So if I ever say a vertical compression, I might mean horizontal stretch, and it could be the same thing. Now, just a little show of why they're equal. So the idea here is that, let's say that I have an A value of 2, but a B value of 1/2 or something, okay? Again, thinking about these, you wouldn't think that they would be equal. Sorry, these would have to be the same, larger than 1. And so these end up actually doing the same thing to the equation because, again, the A value ends up being out front of the function, and the B value ends up being inside of the function. But let's say that the function was x squared, okay? So if f of x is x squared, you basically have a 2 out front of an x squared. But if b is 4, you end up with an x multiplied by a 4, and then that unit squared. If we simplify this, yes, you can simplify it, meaning you rewrite it as 4x times 4x, because that's what squared means anyway, right? You end up with 16x squared. 4 and 4 is 16, and x times x is x squared. So if we look at what a visual of 2x squared and 16x squared do, they are both going to make that same stretch happen. Now, of course, one of them is going to be larger than the other, so it's not that I'm saying that they're going to result in the same stretch, but that they're going to result in the same operation, okay, or change. So either way, that's the idea. You can kind of expand, and that's why it works. So let's go ahead and apply some of this. So we're going to do a stretch vertically by a factor of 3. So stretching vertically is always a lot nicer than horizontally, just because of the whole funky town thing. So if we take a look at stretching vertically by a factor of 3, as we just kind of talked about in the previous slide here, you're going to take your f of x that had an a value out front, and that a value is now 3. So we're going to take that a value of 3 and multiply it by the f of x, which is x squared, and so our new equation is 3x squared. So you just pop it out front, okay? But that means that technically I'm going to do a times my y value, right? So 3 times the y value. So if we apply that in our chart here, I'm going to multiply by 3 and get 27, or 12, or 3. And so when we look at this image, as we're going to make it stretch vertically, I'm now going to take each of these and plot them. So let's see, 1, 3 is here. And then we have 2 up to 12, and then it's mirror. And so hopefully you can see that this is a lot skinnier, vertically stretched. by that factor of 3. All right, so we've got our new equation, our new table values, and also our new image. All right, the next one here is doing a b of 0.2. And so this is where I would recommend, just especially if we look at the table, just plugging it into your equation. So how do we get our equation? Remember that your b value is inside, being multiplied by the x. And so if we end up applying that to our case here, that means that our equation of 3 with an x, that would have normally been here, minus 2, means that that b is going to insert in here. So right in next to the x. Of course, we don't keep it like that. We are going to distribute if we can, so we're going to do 3 times 0.2 times x. And so in that case, 3 times 0.2 is going to be 0.6. So 0.6x minus 2 becomes our new function. So ultimately what I said was that it would be best if you just plug in these numbers into your x and get your new y. It's usually the easiest because technically, and again referencing Funky Town, instead of multiplying your x times 0.2, we're actually going to take each of our x's and divide by 0.2 if we want to kind of jump to the new x value. Okay? So if you want to keep your table the way it is for your y values, all you would need to do is take negative 2 and divide by 0.2, and you'd get your new x value, which would be negative 10. If we divide negative 1 by 0.2, we get negative 5. 0, of course, won't change. A positive 5, and then a 10. So taking a look over here at our graph, the new image is going to be, well, we're centered here still, so 0, negative 2. But then it's going to be negative 5, negative 5, which we don't have on here, so I'm just going to make it up because that's 5, so over here. And then the other one needs to go over 5, so over here. Whoa, that is completely the wrong one. It's over 5 up 1. So over here. And so hopefully you can see that to get to that new image, we did horizontally stretch, which is what the 0.2 is going to be doing. And again, we can reference back to our chart here, but a horizontal stretch is going to be between 0 and 1, and that's what we got for our b value there. So the other way that you could have done this was to keep the table the way it was as your x values. And just plug those x values in to your equation and get some new decimals. So let's see, we could have plugged in a negative 2, so negative 2 times 0.6 minus 2 would have gotten negative 3.2. Negative 1 times 0.6 minus 2 makes negative 2.6. A 0 would have made negative 2. And 0.6 minus 2, if we plug in a 1, makes negative 1.4. And then 2 makes negative 0.8. Is that right? 2 times 0.6 minus 2. Yeah. So as we take a look at those, we can add them to the graph that we already have. So negative 2, negative 3.2, that very much looks like that number. Negative 1, negative 2.6, that's pretty much there. Again, my line was probably not completely straight. 1, negative 1.4, yeah. And 2, negative 0.8. Hey, that was actually really nice. Okay. So, when it comes to your B transformations or your horizontal stretches, it's probably best to not necessarily do the skip to how you would do it, just because they're a little bit more, well, they're funky because they're in Funky Town. So instead, just go ahead and plug in your x values that you already had and then get your new y values to kind of see how it goes. Especially when there's decimals involved, it ends up getting kind of tricky to see the new numbers. But they are nice to see whole numbers over here. So if you can divide by the number that they said was your b value, that can work as well. So those are our notes that you will then try an assignment for.